So in part A, we need to normalize the wave function xi. So that means taking this integral over here, taking the absolute value square of the wave function, this expression should be equal to 1. So we need to set the constant a in such a way such that this requirement is satisfied, such that this integral is equal to 1. So now let's try to calculate this integral, and it would allow us to deduce what this a should be. So the integral goes from negative infinity to infinity, and you can see that from negative infinity to 0, it's just going to be equal to 0 because it does not lie within these two regions. So when from negative infinity to 0, the integral is equal to 0. And then from 0 to a, it is going to be equal to this expression. So we get the absolute value of a squared, x squared divided by a squared dx. And then the integral from a to b, the inside expression is going to be equal to this squared. So we get the absolute value of a squared, and then b minus x squared, b minus a squared dx. And then the rest of the integral from b to infinity, once again, this region does not lie within these two regions, so that's why it's also going to be equal to 0. So the integral from b to infinity is just 0. So now all we have to do is just to focus on these two integrals. So solving this should be easy enough. So I'm just going to pull the constant a squared out first. So integrating this, we get x to the power 3 divided by 3a squared from 0 to a. And then here I'll pull the b minus a squared to the outside. And then integrating b minus x squared, this is just b minus x to the power 3 divided by 3. And since there's a negative sign in front of the x, we need to put a negative sign over here. And this goes from a to b. So now we have to substitute the numbers into the expressions. So substituting a inside this, we get a to the power 3 divided by a squared, so we get a divided by 3. Over here, when you substitute in b, you get 0, so that term is just 0. When you substitute a, you get b minus a to the power 3. And don't forget there's going to be a minus sign when you substitute in the a, so it cancels out with this minus sign. So this is what we're going to get. So you can see that b minus a squared cancels out with 2 of these b minus a's. So in the end, we're left with a plus b minus a divided by 3. So that 2 of the a's, they cancel out. So in the end, you get the absolute value square of the constant a times b over 3 is equal to 1. So this is the condition that we're setting. And so this implies that a is going to be equal to the square root of 3 over b. So this is how you do part A. So this is how you normalize your wave function. You set the capital A to be equal to the square root of 3 over b, and then your wave function will be normalized. So in part B, we need to sketch the wave function. So let's open a new page. So as you can see that, let's say this part is 0, this is A, and this is B. You can see that outside of this domain over here, everywhere else is just equal to 0. And then within this region from 0 to A, you can see that this function goes up linearly. So you get a straight line that goes up. So don't forget this axis is xi of x. This axis is the x-axis. And then from A to B, it goes down again linearly. So that it's going to look something like this. So in the end, you're going to get a triangle. So this is what your xi of x is going to look like. So in part C, we want to find where the particle is most likely to be found. And the probability of finding the particle is related to the value of your xi of x. So the region at the exact point where you're most likely to find the particle is when this function is at its maximum, which is obviously at x is equal to a. So it is at x is equal to a where you are most likely to find your particle. So this is the answer to part C, which is x is equal to a. And then in part D, we want to find the probability of finding the particle to the left of a. So that means finding the particle within this region. So by definition, all we have to do is just to integrate throughout this region from 0 to a. And all we have to do is just to integrate the square, absolute value square of your wave function. So now we can just substitute in this expression. A, we found that it's equal to the square root of 3 over b. So a squared is just equal to 3 over b. And then we have x squared over a squared dx. So integrating this, we have x to the power 3 divided by 3, and you go from 0 to a. And so you get a to the power 3 divided by 3. Obviously these cancel out, this also cancels out. So in the end you get a over b. So this is your answer to part D. So this is the probability of finding your particle within this region. And note that we're also asked to check these two limits. So first we need to check the limit where b is equal to a. So first think about what would happen when b is equal to a. When b is equal to a, you can imagine just moving this point b over to a. So in the end you're going to get something like this. And so you can see that the region from 0 to a is actually the entire triangle. So when b is equal to a, we would expect after we integrate through this entire triangle, we're going to get our answer is going to be equal to 1, because if you integrate throughout the entire wave function, then the total probability must be equal to 1. And if b is equal to a, then from 0 to a you already get your entire triangle. And you can check that when a is equal to b, you do get 1 for this answer. So you can, this is kind of like a consistency check to verify that this solution does indeed make sense. Another thing we can check is if when the case for b is equal to 2a, when b is equal to 2a, you can imagine stretching out this b over to here to a certain point such that this triangle is going to become symmetrical. So when b is equal to 2a, you're going to get a symmetrical triangle. And if you're integrating throughout the left-hand side region, you'd expect this to be half of the region. So this would cover half of the probability. So half of the probability, that's just 1 divided by 2, so that's just 1/2. And once again, you can check this. When b is equal to 2a, you get a divided by 2a, which is equal to 1/2. And so this also checks with our intuition of what this probability might be. So these are just two quick consistency checks for this answer that we obtained.